This video is about the square wave. As you can see, it's a piecewise periodic function, because it repeats, and it oscillates between plus and minus 1. It comes up very frequently as an idealized signal in electronic circuitry, because it's basically an on-off function. It's on, then it's off, then it's on, then it's off, and so on. The dotted lines here represent discontinuities. I've drawn them so you can see the square shape of the function. I've also chosen the period to be 2 and the amplitude to be 1, so that these parts really look square when plotted with aspect ratio 1. But if we scale the amplitude and frequency, or translate the wave in any direction, it would still be called a square wave. We could translate the function up by 1 and then rescale the amplitude by a half, and we'd get a binary signal, 1 or 0. Very precise square waves can be generated by using a vibrating quartz crystal to control the frequency in a microchip circuit, and this is the mechanism that's used in your wristwatch or computer. In an atomic clock, the natural vibrations of atoms can be used to produce a square wave with a frequency greater than 9 billion Hertz. An ideal square wave has a duty cycle of 50%, meaning it's on 50% of the time and off 50% of the time. This is in contrast to a rectangle wave, which can have a duty cycle of less than 50%, like in the example shown here. It's only on for a short time and then it's off for a long time. Rectangle waves are also useful for timing. For example, to reset the electron guns in cathode ray tubes. The rectangular pulse is mixed in with the rest of the signal, which specifies the intensity level of each point on the screen. The electron gun would move across the screen from left to right, mapping out the intensities, and then when we hit one of these pulses, the electron gun would move back to the left-hand side of the screen. Let's now compare the square wave to an ordinary sine wave, such as may be produced by an AC generator. We can construct a sine wave with the same amplitude and frequency. The expression here gives a sine wave with amplitude A, here the amplitude is 1, and with period L. Here I'm showing sine pi x on the same axis as the square wave. Because the two waveforms have the same frequency, they'd be perceived as the same pitch, but they do have distinct sounds. First, let's play a sine wave with a frequency of 440 Hz, which is roughly a middle A. Since this is a single wave with a well-defined frequency, it's perceived as a clean sound. Now let's play the square wave at the same frequency. The pitch sounds the same, but the sound is noticeably less clean. We'll understand the reasons for this shortly. In music playback and recording, you may have heard of a phenomenon called clipping, which occurs when the peak signal level exceeds the maximum capabilities of the system. Here we suppose that the maximum capability of the system is at 1, and the signal goes all the way up to 2. The excess part of the signal is cut off, resulting in a flattened waveform, which has similar properties to a square wave. If the signal is the voltage being delivered to an amplifier, then we say that the system is overdriven. The sound is not as clean as the pure sine wave, although still not as distorted as the square wave. It will sound a bit different depending on your speakers. On mine, it has a noticeable buzzing sound. Now let's go back to our 440 Hz sine wave. The wave is represented by the function a sine omega x, where omega equals 2 pi over L, and L is 1 over 440. What's shown on the graph here is a single period. If we multiply the frequency by an integer n, then we get n full periods within one period of the original wave. So here's what happens if I multiply by 2. The blue wave has frequency 880 Hz. There are 2 periods within one single oscillation of the 440 Hz wave. If we take n equals 3, we get 3 complete periods, and so on. These integer-scaled waveforms are called harmonics, or overtones. The original waveform is referred to as the fundamental frequency. If we double the fundamental frequency, we get the second harmonic, which is also known as the first overtone. This is the third harmonic, or second overtone, and so on. Harmonic series are very important in music. Here are the first 3 overtones that correspond to a fundamental frequency of approximately 131 Hz, which is an octave below middle C. This is the first overtone, the second overtone, and the third overtone. They are the first 3 notes played in a piece of music that was popularised by its use in Stanley Kubrick's film 2001: A Space Odyssey. Do you recognise it? Now, if we add together harmonic components, like these, the result will clearly be periodic as well, with the same period as the fundamental frequency. Let's look at what happens if I sum just the odd-numbered harmonics. Here's the fundamental, 440 Hz again, and here's the result for summing the first few odd harmonics. The formula is given here. I'll play the 440 Hz fundamental again so that you can remind yourself what it sounds like. And here's the result for the summed harmonics. So clearly, again, the result is not similar to the pure tone, but it does have the same frequency. We can contrast this with the case where the summed waves are not harmonic multiples of the fundamental frequency. Here I've summed a bunch of waves with randomly chosen frequencies, together with the same fundamental 440 Hz wave. The resulting audio spectrum is non-periodic, although it is close to a periodic function. It has a characteristic bell-like ringing sound. Finally, let's have a look at what happens to the odd-numbered harmonic series if we scale the amplitudes by 1/n. So here I've summed up the same waves as before, but I've scaled the amplitudes by 1/n so that the fundamental is dominant and the higher frequency waves all have decreasing amplitudes. You'll notice that the plot of this function starts to resemble the square wave, but it has a longer rise time, it's not instantaneous, and it has noticeable secondary oscillations. Let's have a listen. And let's look at what happens as we increase the number of terms. The rise time starts to decrease, and the secondary oscillations are damped out everywhere except near the discontinuities. The behaviour near to the discontinuities is a mathematical artifact, not some numeric error, which is known as Gibbs phenomenon. In a limit as the number of terms tends to infinity, the affected domain becomes narrower and narrower, but the size of the over and undershoot behaviour approaches a finite limit. Audibly, the effect of Gibbs phenomenon in a digital system is a ringing burr, although not as pronounced as what we heard with the non-harmonic series. Listen carefully for the background ringing as I play the sound. This result should satisfy you that the ideal square wave contains an infinite number of frequencies. We can plot a power spectrum for the square wave. The power spectrum shows the amount of power contained in each of the harmonic components, so this is the power contained in the fundamental. The power contained in all of the even-numbered harmonics is 0, and the power contained in the odd harmonics decays with n. For sure, the power contribution decays quickly with n, but this is actually an atypically slow convergence compared to the harmonic content of continuous functions, or functions that have a gentler discontinuity. In fact, it's possible to show that a significant fraction of the signal's power is contained in the high-frequency components. 5% of the power is contained above n equals 9. The fact that the power is spread over a wide range of harmonics explains the crunchy sound of the square wave. Also, high-frequency harmonics are subject to distortion when transmitted over ordinary fibre optic cable, so telephony systems are bandwidth limited to reduce distortion. A low-pass filter only allows low-frequency components to pass through, so the square wave is approximated by the first few terms in its harmonic series, and we end up with something like this realisation here.